Hey everyone, let's start Chapter 2. Our topic today is system identification using machine learning. Before we even dive deeper, think about this. Almost every real-world system has behavior that changes over time: motors, temperature processes, chemical reactions, and even heating or cooling systems. That's why engineers often prefer a method that can learn the behavior. Machine learning gives us that ability. It can capture patterns without us defining the exact mathematical equations. Simply put, it's the process of building a system model directly from input-output data.
So we don't need complicated mathematical equations anymore, Doc? I mean, that sounds almost too simple, right? Like just feed it data and it figures everything out?
Exactly. If the system is difficult to model, we just provide a dataset. ML will learn the dynamics automatically. This approach is called data-driven modeling. It means the model discovers the relationship between input and output by itself, without us writing down any differential equations.
So ML basically mimics the behavior of the system. Does that mean if the dataset is bad, the model will also behave badly? Like garbage in, garbage out.
Correct. ML predicts the system's response based on past patterns. Once trained, the model can even predict how the system will react to new inputs it hasn't seen before.
What kinds of ML models are used for this, Doc? I'm guessing different models work better depending on how complicated the system is?
A basic one is the multilayer perceptron. But if the system has time-dependent behavior, models like recurrent neural networks work better. Because they can remember. RNN works well for any process where the current output depends on the past, like temperature control.
Oh, so they're suitable for systems where the output depends on previous conditions. Like if a system is slow to respond, the model needs to know what happened right before, right?
Exactly. That's why system identification is important in modern industries. Fast, flexible, and able to handle non-linear behavior. Because industries today generate massive amounts of data, ML-based system identification becomes easier, more accurate, and more practical than ever. So instead of spending weeks building equations, engineers can train an ML model in minutes or hours. This not only speeds up development but also improves accuracy, because the model adapts to real measured data, not assumptions.
All right, Doc, the basic concept makes sense now. I didn't realize that building a model without equations could be this practical. Honestly, it feels more practical than I expected. I thought modeling systems was always full of heavy calculations.
Yeah, this actually makes the whole idea of modeling feel more accessible. I thought it would always involve heavy math and many other complicated things. This approach feels more approachable, especially for students who are just getting into control systems.
Good. That's why understanding this chapter is important. It prepares you for more advanced control methods later on. And when you grasp the basics, you will master it easily. Once you understand how data-driven models work, it becomes much easier to design controllers, predict behavior, or even create digital twins for real systems. Alright, moving on. This video covers the workflow of system identification with ML. Just a simple step-by-step flow. The workflow is quite similar to regular machine learning, but the focus is on learning time-dependent behavior. Even though the workflow feels similar to standard ML, the emphasis here is that we are trying to learn time-dependent behavior, not just static relationships.
Okay, so the workflow is pretty similar with the regular machine learning. In this case, where do we start, Doc?
First, we collect input-output data. This is essential. ML needs examples to learn. The data also has to be diverse enough so the system's patterns can be captured. Usually, the more variation in the data, the easier it is for the model to truly understand the system's dynamics.
Right? So the model won't learn properly if we only collect data from one type of system behavior?
Exactly. If the data is too limited, the model only learns a narrow slice of the system's behavior. It'll look good during training but fail in real scenarios.
Kinda like studying only the examples from your homework, but then the exam questions are different.
Yes, perfect analogy. In control systems, variation is crucial because different inputs reveal different dynamics.
After we collect the data, we do pre-processing, right?
Yep. Usually normalization and noise filtering. This helps the model learn more reliably. Sometimes we also need to synchronize the data or remove outliers so they don't interfere with training.
And sometimes sensors give spikes or drift, so pre-processing cleans that up.
Correct. Real-world data is rarely clean. Sensors can lag, vibrate, overshoot, or misalign. Pre-processing fixes these issues.
So if pre-processing is sloppy, even a great model will perform badly?
Absolutely. Many failed identification attempts trace back to poor data preparation.
Then, after we pre-process and synchronize the data, we choose a machine learning model.
Correct. If time relationships matter, choose a model with memory like recurrent neural network or RNN. If it's simpler, and multi-layer perceptron or MLP works too. The model choice depends heavily on how complex the system is and how good the data quality is.
So if the system depends heavily on its past states, we should go for something like an LSTM?
Yes, LSTMs and GRUS handle long-term dependencies very well, but they're unnecessary for simpler systems.
What about transformers, Doc? People use them everywhere now. They can be used, but they need huge amounts of data. RNN-based architectures are still the practical choice for most engineering systems.
And then we just train the machine learning model we choose. Is that right, Doc?
Yes. The model learns by minimizing the error between predictions and real data. After that, we evaluate it using test data to check whether it truly understands the system dynamics, not just memorizing the training data. If the model memorizes instead of learning patterns, that's called overfitting, and it happens a lot when the dataset is small.
If after we do the testing and the results are bad, we tune it.
Exactly. Tuning is normal. Adjust parameters, add data, or switch models. In industry, tuning can often take the longest time because finding the optimal settings isn't always straightforward.
All right, Doc. The workflow is very clear now. Turns out it's pretty similar to normal machine learning, just applied to dynamic systems.
Welcome back. This is our final video for Chapter 2. Today we are going to look at two important models used for dynamic system identification, NARX and recurrent neural networks, or RNNs. Both of these models can capture time-dependent behavior, which is something regular static ML models simply can't do.
Doc, I've heard the name NARX before, but I never really understood it. What exactly makes it special?
Great question. NARX stands for Nonlinear Autoregressive with Exogenous Input. It's a model that predicts the output of a system using past inputs and past outputs. Imagine you're trying to guess what will happen next by looking a few steps into the past. That's basically how NARX works.
So if a system's behavior depends on what happened before, NARX can pick that up.
Exactly. Think of something like room temperature. If the room was hot a few seconds ago, it won't suddenly become cold instantly. Its current temperature depends on the previous state. NARX captures that kind of dependency very well.
Is NARX similar to those classical autoregressive models?
Yes and no. It's similar in the sense that it uses past values, but the big difference is that NARX is nonlinear. That means it can represent more complex system behavior than traditional linear autoregressive models.
All right, got it. Now what about recurrent neural network or RNN? They sound more modern. Are they like NARX 2.0?
In a way, yes. RNNs are more flexible because they have something called a hidden state, a sort of internal memory that gets updated over time. This allows RNNs to understand long sequences and complex temporal patterns.
So RNNs can remember things from way earlier in the sequence?
Exactly. Plus, there are improved versions like LSTM and gated recurrent unit, which can remember information much longer and handle training more reliably. These models are amazing for processes that have long-term dependencies, like chemical reactions, thermal processes, or even vibration data.
But I've also heard RNNs can be heavy to train. Is that true?
Absolutely. RNNs usually require more data, more computation, and more training time. For simpler systems, using an RNN is often overkill. That's why many engineers still prefer NARX if the system isn't too complicated.
So it really depends on what kind of system we're dealing with?
Exactly. If the system has short-term relationships and is relatively simple, NARX is usually enough. If the system has long-term dynamics or very complex behavior, RNN or LSTM is the better choice.
I like that both options have their own strengths. They're like tools for different jobs.
That's right. And the cool thing is, even with just NARX and RNN, you can already build a simple digital twin, predict system behavior under new inputs, or even prepare the model for control applications.
So learning these two models helps with future topics too?
Definitely. Once you understand these dynamic models, it becomes much easier to move into things like adaptive control, neural network controllers, and even reinforcement learning in later chapters.
Nice. This chapter really helped me see how machine learning can handle real dynamic systems.
Same here. NARX and RNN finally make sense now.
Great. That wraps up Chapter 2. In the next chapter, we'll start exploring more advanced control methods that build directly on what you've learned here. See you in the next video.